Hey guys, welcome back to another video in this series on quantum computing. So we will continue working on the Bernstein-Vazirani problem, and now we will look at the quantum solution. Now this quantum solution is a bit tricky. It requires a bunch of math and some non-intuitive concepts, so I think I will dedicate this whole video to just the theory of the solution, and then I'll relegate the coding it up part to our next video. So it's a bit complicated, the solution, but just bear with me. I'll try to make it easy and um, yeah, let's see let's see how well I do. All right, let's begin. So, like I said in the previous episode, or rather, let me actually step back and remind you what the problem was. So, given an oracle which takes in a string x and returns this, the dot product of the string and um, and a secret bit or a secret string, and then whatever the dot product is, mod 2. So that's what this black box or oracle returns. And the task is to find this secret string. In the classical way of doing things, we saw that if we made n queries, where n is the number of bits, and all the queries were one-hot vectors, you could decode this secret string. But my claim, or rather their Bernstein-Vazirani's claim, is that we can do it in one shot or with one query. So let's look at that. Um, Before we even look at the solution, the first thing that we have to do is convert the oracle. So if you remember from the previous video, we coded in a classical oracle. Now we need to have a quantum oracle. So I want to tell you some properties that a quantum oracle has. So you can take them as facts, but and I will try to prove one of them. But the main property is this, the first one, where the oracle acts on a state. It basically gives you -1 to the fx of that state. So this is the action of the oracle, the first one. Now the way it works is, again, I won't go into the theory. It also, well, I will tell you how it works, but there is also this property where if I have a state x and I have an auxiliary state y, the action of the oracle on this combined x outer product y state is x remains as is, and then I get it XORed with, rather C naughted with y C naught f of x. So this is my outer product, not a plus sign. Sorry for that typo. But x outer product y C naught f of x. That's a property, just take it as a fact. It has to do with how to make quantum circuits reversible. That's why you need an auxiliary bit, but let's just assume these two things as facts of quantum computers. So I again want to stress the second property where if you have, so x is your real state, y is just, throw away auxiliary temporary qubit state. The way the oracle acts is whatever your y is, it gets C naughted with f of x. That's it. All right. So this is a property which we will use to derive the first one. So again, the proof is not important. If you just want to take these two as facts, go with that. But in the next few minutes, I'll try to explain how action of one comes about. So, well, these two are exactly the same thing. It's just one is a specialization of two. So the property that you need to care about is that when you act x with an oracle, it gives -1 to the f of x. Now x again is a string of 0, 1, 0, whatnot. It's just a string of bits. So let's look at the proof. Now let's say I start with, um, let's see, let me just zoom out a bit. Okay, so let's say I start with my state xy, where y is the auxiliary one, and then the action of oracle, like we saw, would be this x, and then y gets C naughted with f of x. So this is my equation 1. Now suppose my auxiliary was a minus state. If you remember, minus state was 0 minus 1 divided by square root 2. So suppose my auxiliary is this, then what would happen is, all right, so for the 0th state, f, so first I have to compute what f of 0 is. So, right, sorry, what f of x is. So, right, so, well, my bad. I've just replaced the minus with the value of this state. So minus is 0, minus 1, square root 2. So here I have just replaced it here. Now I apply the second law, which on like basically this equation to this state, where I get x has the first one gets 0, then a C naught operation on f of x, and then the same thing with the 1 state, 1 C naught, and then of f of x. So that the the control bit is the second one. So the control bit is f of x. Now, depending on the value of f of x, we flip the target bit. So if you remember, C naught gate has a target and control, and depending on the value of the control bit, sorry, the target flips. So if the control is 0, the target doesn't flip. If the control is 1, the target flips. So my control is the second element. F of x is my control. So if f of x is 1, then what I get, this flips and this does not flip. So, sorry, give me one sec. Yeah, no. If f of x is 1, that means both of them flip. This becomes 1 and this becomes 0. So that is basically the negative of my current state. So you get a minus 1. You can rewrite this whole result as a minus 1 x of minus state. If my fx is 0, that means there is no flip, and I just get x, and this should be a minus. So let me just make it a minus. To make it big. Yeah, so let me just drag it up. Yeah, so basically I would just get a positive value. So basically, if my second auxiliary bit was minus state, the action is this, like x basically goes to minus 1 to the f of x. On both sides, there is the auxiliary bit floating around, but we don't care about it because it's a temporary variable and we can forget about it. That's why it's not written here. So again, so this is how this oracle works. The oracle acts on your state, and then basically it adds a phase value of minus 1 to the f of x on your state. Okay, that's how a quantum oracle works. So now let us go down, or rather move on to the solution. Okay, so in this solution, we first start with all zero state. So if we want to decode the n-bit state of the secret um, string, we start with an all zero state. So here I have an all zero state to start with, and then I apply a Hadamard to each of the strings or each of the bits. And I have shown only like 3-bit example here, but you can just apply that to n-bit examples. So starting from an all zero state, you apply Hadamard to each bit. Now you also have this auxiliary bit, and this auxiliary bit is used in this oracle computation. So once Hadamard has been applied, you apply the oracle to, so this whole combination is the oracle, and then I apply Hadamard again to get back my state. And it turns out when I apply Hadamard again, I get back the secret string, not my original state. I get the secret string, and I will show you why that works. So first of all, the reason why you apply Hadamard twice is because Hadamard is its inverse. So H give the same state back. So if you apply H, you need to go back to the original basis of states. So that's why you apply H again. That's why two Hadamards, and in the middle you apply this or a quantum oracle. So To begin with, you always apply H because the Hadamard basis is a better basis for all this computation, and our oracle is written in the Hadamard basis, so that's why. Good. So let's look at how it works. So first, I start with an all zero state, and then I apply Hadamard to each of my bits. That will give me a combination of states. So that gives me 2 to the n states, and I represent this by just the letter x, where x is it could take 0 or 1 raised to n being like n different bits. Okay, as an example, if I have a 2-qubit state, applying Hadamard gives me this combination. So each bit you apply a Hadamard, and then when you multiply them out, this is what you get. And the same thing for 3-qubit states, 4-qubit states, and so on. Now, let me tell you this property of Hadamard. I said Hadamard gates are self-inverting. By that I mean Hadamard is its own inverse. So H inverse is just H. If I start with an arbitrary state and I perform a Hadamard transformation, I get um, I get this state -1 a dot x, where x is 0 and 1. Now, so say if it's a two-bit state, x would take all possible 2-bit values, and then that's how this is my shorthand. Now this a dot x is basically a phase that gets added in, basically the dot product between a and the current value of x. So if you write it out, so here in this 2-qubit example, because 0 maps to 0 plus 1, that's why all the terms are positive. But if you remember, 1 maps to 0 and minus 1. So that's where you can get like plus and minus signs. So then if it was 0, 1, I would get some terms to be negative, and that's what this means. So if you just map it out, the Hadamard action on any n-bit state can be represented like this. Now, if I again take the inverse, I should get my original state back. So I get my A back. Intuitively, this makes sense. So I start with A, apply a Hadamard, I apply Hadamard again, I get my original state back. Good. So this is like encoding, and the second application is like decoding. Good. So I want to stress on this fact that um, after it was encoded, the actual bit gets encoded in this exponential. So it's -1 to the power of -1. So a dot x is this. So this actual bit gets mapped here. So when you go back, whatever is the coefficient of x here is what gets mapped back. Just a point to note for the future. Good. So now that we have this state, this one, now that we have applied our Hadamard gate, let's apply the oracle. So the action of the oracle was just to add this phase factor. Now, what did oracle do? Oracle added this -1 to the f of x. And f of x, remember, was just s dot x mod 2. So let's go back to, where is it? Yes. So when I apply the oracle on this x state, I get s dot x. All right. And now I apply my inverse Hadamard transformation again, and whatever is the coefficient of x gets mapped back, and that's why I get s back. Because if you remember from here, a dot x gets mapped back to a, because multiplying x is a, and here multiplying x is s. So when I do an inverse Hadamard or a Hadamard again, I get s. So instead of passing in multiple queries, we did it in a single shot fashion. Just one shot, and that gave us the result. So basically, let me summarize this again. I need to start with a state of all zeros, apply Hadamard to all of them, and then also have an auxiliary negative state hanging around. That is used to apply the oracle on this encoded state, and then we decode it and we get our string back. Just a single shot I need to pass in the zeros, all zeros just once, and I get all my bits. That's how it works. All right, so this video has been going on for 15 minutes. I'll stop here. In the next video, I will start with an example, and I will also show you how to code this up. I know this was a lot of math, but maybe the example that I will show you the next time will make it a bit more clear and obvious. All right, see you next time.